In this video, I'm going to be telling you about exponential functions. And I'll start by telling you what an exponential function is. An exponential function is a function where the independent variable is an exponent, right there. It's like a times b to the x, where a and b are real numbers. In this class, we're going to be concerned with situations where b is a positive number. But, maybe in a different class, you might be interested in situations where b was a negative number, in a more discrete scenario. Okay, but up to this point, the functions we've looked at in this class have all been power functions. So let me just copy a couple of those in there for you. So the main four function types we've studied in this class have been quadratic, cubic, square root, and cube root. And we know that the graph of y equals x squared makes a parabola, y equals x cubed. That wasn't the best one I've ever drawn, but that'll do. Y equals square root only has, kind of like half of a graph. And y equals cube root x has the whole thing, and it goes like that. That's not very good either. Okay, but these are kind of the power functions that we've seen. And what we learned recently was that, we could write square root x as x to the positive 1/2 power, and cube root of x was x to the positive 1/3 power. And what I want to point out about these is that x is the base of the exponential expression. So that's what makes it a power. It's, some power of x. Whereas an exponential function will be something like, g of x equals 2 to the x. That'll be one we're definitely interested in. Another one we're interested in Algebra 2, at least in Texas, but I think in all Algebra 2 classes, is 10 to the x. And then there'll be this other function we'll talk about later on, or maybe in the next video, called e to the x, where e is just this number like 2.7 something that we happen to be interested in. But just to emphasize, like what makes these exponential functions is that x is in the exponent, right, for all of these. All right, now let's graph one of these things, see what the graph of an exponential function looks like. So we're going to make a table of values and sketch the graph of y equals 4 to the x. Okay, now I already know that you know. All right, so there we go. So I've, plotted my points, and I'm not sure if the recording cut out when I was doing my computations, but, in case it did, it's all over there. Work is shown. And now I'm going to connect the dots, right? Because that's how we can always sketch a graph, is make a table of values, plot points, and connect the dots. Okay. Okay, I'm just going to kind of see this over here. Now we also know that this is going to be an increasing function. I'm going to zoom out a second. Because the bigger exponent we put on 4, the bigger the result is going to be. So this thing's going to continue to increase. Okay, and this is going to kind of continue along that same shape where it's just curving upwards. And I can also put a y-axis in because I know that's going to be where x equals 0. And I'll just maybe label that as y equals 1 there at the intercept. And that's going to be the shape of our exponential growth curve. But before we move on and graph another exponential curve, I want to point out about the domain and range. So the domain of an exponential function is going to be all real numbers, because there's not really anything that I could put into x. There's no real number that I could plug into x that would be a problem. We can take forward to really any power that we want. Okay, so the domain is going to be all real numbers. And then the range of this function, you can see from the graph, the actual y values that are achieved, y is just greater than 0. But we've also seen that in this class, right? That if we take a positive number to any power, we're going to get a positive number back. I'll let you think about why that's true. But all the same, this is going to be, kind of the typical domain and range for our exponential function, or at least kind of the base case. Now let's graph y equals 1/2 to the x. And I'm going to just, bring in the table of values real quick. And, this is kind of like before, 1/2 to the first, 1/2 to the second, 1/2 to the third. I expect you're probably good with those. 1/2 to the 0, you need to be reminded that's equal to 1. 1/2 to the negative first is 1/1/2, and, 1/2 to some other negative power would be 1/1/2 to that power. And so we're getting 2 and 4 and 8. So let's just, plot these points. And then I can connect the dots. And I'm thinking I might kind of do this in 2 pieces. No. Always when I end up doing it in 2 pieces, the graph doesn't look very good, but it's always kind of tough to sketch on a tablet. So getting that good curvature. This is looking better than I expected it to. Let me zoom out a second. Right, that's looking pretty good. I'm going to bring in a y-axis. Come down through here. I'll label that y-intercept here in a second. The y-intercept was when x is 0, y is equal to 1, and so there I've got myself the graph of y equals 1/2 to the x. Notice again the domain's all real numbers because there's no x's that we can't put in as an exponent. Also, the graph is extending both directions, left and right. It's not any breaks or holes or anything in there. And the range is y is greater than 0 because they're saying the graph is only staying in the first two quadrants, above the x-axis. Okay, but again, we're taking a positive number to differing powers, and you take a positive number to any power, you're going to get something positive back. All right, now these two graphs that we've produced are kind of showing you the two typical cases for exponential functions. Now there are other things that can happen that we'll probably talk about in a pre-calculus class where you get like a 1 over 1 plus 2 to the negative x or something, where you get a negative exponent in the denominator, but with something added to it you can get a weird shaped graph. But for us, we're going to be interested in exponential growth and exponential decay. And we saw that 4 to the x and 1/2 to the x are both exponential functions, but they have these very different looking graphs. We're going to say that an exponential growth function is one where the base, the number that's getting taken to the different powers, is bigger than 1. And exponential decay is going to happen when that base is less than 1. Now, in this class, we're going to be interested in where b is also greater than 0. And you probably also saw this with the other graphs, but with exponential growth and decay, they have this horizontal line, the graphs do, that they approach but are never able to touch. And this is something we're going to talk about more in this class, but this is right here, in our examples it was y equals 0, but that's not always going to be the case in general. And that line is something that we're going to call a horizontal asymptote. And now we're going to talk a little bit about asymptotes later on in this course when we study rational functions, but for now I just kind of want you to have heard that terminology, that this is a line that the graph is kind of like approaching but not touching. We'll talk a lot more about this kind of in the next unit, I think, maybe the unit after that, I'm not remembering, but for this class we're just mainly going to stick with the domain and range questions. So let's sketch another graph. So let's look at y equals 3 to the negative x and see what's going to happen there. So 3 to the negative 1, we're just going to make a quick table, and I can do this with you watching. That's 1 over 3. 3 to the negative 2, if I plug in x equals 2, that's going to be 1 over 9. 3 to the negative 0, that's just 3 to the 0, it's going to be 1. Okay, and if I plug in negative 1 there for x, it's going to be 3 to the negative 1 is 3 to the first, that's equal to 3. And then if I plug in negative 2, I can see what's going to happen. I'm going to have to take 3 squared, that's going to be 9. I'm going to plot these points. And then I can connect the dots. And we'll see that this is supposed to be an exponential decay situation. And not my best drawing ever, but it's okay. One thing that I would point out to you is, it's going to decay more rapidly than 1/2 would, because this is 3 to the negative x. And, I'm going to sketch a y-axis, because that's probably the right thing to do. Though this is very, very crooked. Let's try that a second time. This will be better. Okay, 3 to the 0 is 1. Okay, so I've got myself y-axis. And what I was going to say is this is an exponential decay. We can see based on the curve. But I could also do a little bit of work on the exponents and say, okay, well, y is equal to 3 to the negative x. And say, well, negative x, that's negative 1 times x. And I could say, well, that's the same as 3 to the negative 1 to the x power. We know what 3 to the negative 1 is. That's 1/3. So this function, 3 to the negative x, this is the exact same thing as 1/3 to the x. So that's why it has a similar graph to y equals 1/2 to the x. So just, be aware that for, when I'm saying that the base is greater than 1, or the base is between 0 and 1 for these growth and decay scenarios, I'm assuming a positive x in the exponent, right? If we see a negative x, then that would kind of reverse the situation. Alright, now for kind of a brief interlude, we're just going to solve a couple of basic exponential equations. Not This was something we needed to do today, but I didn't really know where to fit it in, so I figured I'd just put it right in the middle, just kind of give you a break and give you something more familiar. So the thing here is if we have like the same base and two expressions and they're set equal to each other and they're both exponential expressions, we can just set the exponents equal to each other. Like over here, what I'm saying is I'm gonna say x plus 3 has got to equal 3x minus 5 because there's not, some situation with exponents where we can take two different exponents and get the same result back. That's not going to be possible if you think about it. So I'm going to say, okay, if 2 to the x plus 3 equals 2 to the 3x minus 5, then that means that x plus 3 has to equal 3x minus 5, and that's something we're good at solving, right? I'm going to subtract 1x from both sides. And then I'm going to add 5 to both sides and divide by 2 and see that x is going to equal 4. In the second example, I'm going to look at this and, okay, these aren't exactly the same exponent, right? I've got 3 to the 2x plus 7 equals 81. Okay, that's not an exponential expression, but 81 is a power of 3. So I can say 3 to the 2x plus 7 equals 3 to the 4 that's what 81 is. Okay, and then I can say, okay, well, 2x plus 7 equals 4. 2x equals 3, and x equals 3 halves. Okay, this third one, oh, I like this one. I'm glad this one's on here. Okay, I got 4 to the x plus 1 equals 8 to the x plus 2. And you look at this and it's like, it's not the same base. And you might say, oh, because 8 is 2 times 4, like it's a multiple of 4, that would be what we work with, but we're actually going to work on the fact that they're both powers of 2. Okay, because we really need to be sitting in our exponent rules. The exponent rules are going to be so crucial in this unit. So I'm going to go over here and I'm going to say, okay, remember that 4 is equal to 2 to the 2. And 8 is equal to 2 to the 3. Okay. So I'm going to say, all right, I had 4 to the x plus 1. Now I've got 2 squared to the x plus 1. That's going to equal 8, which I'm going to write as 2 to the 3rd now, to the x minus 2 power. And remember, when we have like power of a power, that's where we're going to multiply the exponents. So I've got 2 to the 2 times x plus 1 equaling 2 to the 3 times x minus 2. And so I'm going to, at this point, say, okay, I'm realizing that the exponents need to be equal. Okay, I've gotten to the same base. So I'm going to go, and I might distribute in this step too. So if I distribute the 2 over the x and the plus 1, I'll have 2x plus 2. And that'll equal 3x minus 6. And then I'm just going to solve for x, like I'm accustomed to. I'm going to add 6 to both sides. I'm going to subtract 2x, and I'll see that x is going to equal 8. Man, these are great equations. These are equations you need to be able to solve. We're going to do some practice on these, but there are other more interesting equations for us to solve in this unit that I'm much more excited about, so I'm just going to move on. So let's sketch another graph. This one, I think we're going to be able to go a little quicker with this one. We've dealt with enough exponential functions now that we can say that because it's 1.5 to the x and 1.5 is bigger than 1, we're going to be seeing exponential growth. And we know that the graph of exponential growth looks like that. It curves up pretty strongly. And 2 times 1.5 to the x, 1.5 to the x, that's going to happen first before the multiplication because of PEMDAS, exponents before multiplication by 2. This is going to be a positive number because 1.5 to the x is positive. Make it multiplied by 2, it's just going to be twice as positive. So I know that the x-axis is going to be right here. Really, the y-axis probably go about wherever. I'll just put it in right here, kind of in the middle. Okay, and what I would say, with this question looming down below, what's the impact of a on the exponential function? Well, let's just plug in x equals 0. That's what I want to get at. So at x equals 0, y equals 2 times 1.5 to the 0. Now, I said it before, but I'm going to say it again. I'm going to say it pretty repeatedly here. Okay, think about PEMDAS. Okay, exponents before multiplication. So I have to do that 1.5 to the 0 first, and then I'll multiply that result by 2. So 1.5 to the 0 is 1, meaning I've got 2 times 1, and that's going to be 2. Okay. Now the other exponential functions we've seen didn't have some multiplier in front of the exponential bit. By the exponential bit, I mean the thing that's getting taken to the x power. Oh, that. Okay, we saw that they had y-intercept 1, and this is having y-intercept 2. And, it's not some big mystery. It's because of that multiplier of 2. Okay, so the impact of a on the exponential function f of x equals a times b to the x, you might describe it as a vertical stretching factor, but you might also just look at it as a number that's going to change the y-intercept, and I actually kind of like that a little bit better because I want to think about a closely related function to this one. What about y equals negative 2 times 1.5 to the x? Like, what would happen there? And that would also change the y-intercept, and I feel like that would actually give you a pretty good idea of what was happening there. Think about, it's just everything get multiplied by negative 2, everything would become negative. So it would flip this graph upside down. And I just actually copy-pasted that thing and did flip vertical. But, it's going to be the same thing, right? Because all the y's became negative at x equals 0, y is going to equal negative 2. And we're still going to see that exponential growth, just growth in a negative direction. So I just wanted to show you one of those. So I might add on that, a could flip the graph vertically if a happened to be a negative number. Alright, now we've got another one, y equals 2 to the x plus 1. Okay, this one, okay, yeah, kind of the same thing. Okay, it's going to be exponential growth. And we know what the shape of an exponential growth graph looks like, provided it's not multiplied by a negative number. Okay, it's going to have, obviously a different y-intercept than it would if it was just y equals 2 to the x, because we've got this additional computation, right? Maybe I'll go and I'll do that now. X equals 0, y is going to equal 2 to the 0 plus 1. I don't think, people would be at risk of doing this in the wrong order. People are going to know to do 2 to the 0 first. That's 1 plus 1, and that'll equal 2. Okay, so I'll just decide, I guess that's going to be my y-intercept. That will be at y equals 2. And I can bring in a y-axis here. But all of these y-coordinates are going to be kind of bumped up by 1. And we already, I don't think we graphed 2 to the x. We graphed 4 to the x, and, very similar graph. And we saw that it kind of approached y equals 0. It approached the x-axis as x went towards negative infinity. And so that's not going to be the same anymore, right? Because really what we're seeing is as x approaches negative infinity, let me go off to the side and one note. Yeah. As x approaches negative infinity, 2 to the x is approaching 0 because 2 to like a really big number that's negative is going to be 1 over 2 to a big number. And if we're taking 1 and dividing it by something huge, we're going to get something really small back, right? So I've got something that's getting closer to 0 plus 1 after. So that's going to be getting closer and closer to y equals 1. And, earlier I told you that line was called a horizontal asymptote. And I'll just draw that in. Most people draw asymptotes with a dotted line. I probably should have done that earlier. And so if they ask what's the impact of c on the exponential function f of x equals a times b to the x plus c, I might say that it moves the horizontal asymptote, but that would really be kind of a symptom of what's going on, not really the cause. Really what's going on is that, kind of we've undergone a vertical shift, because the function was one thing and now we're adding 1, so we're getting shifted up by 1 from what we would expect if it was just y equals 2 to the x. But another thing that's happening here is it's going to impact the range in a way that that multiplier a does not. Okay, so on this graph, the range of the function is y is greater than 1, right? Because y equals 1 is a horizontal asymptote, or because 2 to the x plus 1 is, some positive number plus 1, which is always going to be bigger than 1. So over here, the range of our function is going to be y is greater than 1. And that's because of the plus 1 right there, that value of c. Now in this class we are going to be interested to a certain extent with how we can use exponential functions to model real life scenarios. And exponential growth and exponential decay are decent models for certain phenomena in the real world. Okay, and so what we've seen is that exponential growth happens when the number that's getting taken to the various powers is greater than 1. And that's what we're showing right here, that a times 1 plus r to the t is exponential growth. And that fits with what we've said, right? That we see exponential growth when the base is greater than 1. And then over here, a times 1 minus r to the t, that's going to be exponential decay, because we're seeing b is between 0 and 1. I was going to do that as an interval, but I think it would be clearer to say the base is between 0 and 1. We'll say that number r, that's going to be the growth rate or the decay rate. And we typically express these decay rates or growth rates in percentages. And I'll show you what I mean here with an example. But wait, I don't think I really gave you a good idea of what the other variables meant. We saw what r meant, but a is going to be generally representing some sort of like initial population, some starting value. And y and t will kind of just be like the output and input values, like y and x, where y is the population or amount, and t generally represents time. So, all right, so now that I've told you what all the variables mean, now let's go ahead and look at an actual example. All right, so for example, look at these functions and determine whether they represent exponential growth or exponential decay. We know that'll be relatively simple. Look at the base of the exponential expression, see if it's bigger than 1 or less than 1. And then we'll find the rate of growth or decay, and that's kind of the thing that would be new to us. So I'm going to go over here and I'm going to say, right, starting with 6 times 1.04 to the t. 1.04 is greater than 1, so I'm going to say exponential growth. Okay, and for exponential growth, we said it was a times 1 plus r to the t. So what I'm going to do is I'm going to kind of rewrite this as 1 plus something to the t. So 1 plus 0.04 to the t. And then r was our growth rate, so it's 0.04, and that's 4%. Okay, so let's say 4% growth. And yeah, f grows by 4% every time t increases by 1. And g of t, that's going to represent decay because the base of the exponential expression is 0.76, and that's less than 1. Okay, so I'm going to say that this is 1.62 times 1 minus something, and I need to figure that thing out so that I can figure out the decay rate to the t. Now, if you're having trouble figuring out like what would go in there, we can just kind of like set up an algebra equation. Okay, we can say 1 minus r equals 0.76. Okay, so I could subtract 0.76 from both sides, and I'd get 1 minus 0.76, add r to both sides, and okay, I mean, yeah. If you didn't just see it like that, I was saying that this is something we could solve for algebraically. Either way, you're going to see r needs to be 0.34, no 0.24. See, that's the risk in the arithmetic there. And so that 0.24 number there, that's my decay rate, and I would say that is 24% decay. And h of t, I'm going to just do this one real quick. This is going to be growth because that number is bigger than 1. That's 1 plus 1.14 to the t, multiplied by 4.6. Okay, so that 1.14 is the growth rate. And so what we would say is that's 114% growth. But I'm assuming you have seen stuff like this before. Percent growth, previous algebra class or previous math class. All right, now in conclusion, I'm going to bring in an actual example with some kind of meaning. So a house in the area over the past 10 years has seen its value grow by 8% per year. 10 years ago, the house was worth $200,000. And so we're going to write a function that represents the value of the house over time. So I'm going to start by defining my variables. So I'm going to let y represent the value of the house in dollars and t represent time. And so what I showed you earlier was kind of a skeleton formula that you could use. It's going to be y equals a times 1 plus r to the t. Okay, and we're seeing growth. Let's see the word grow. Okay, I don't think that you will see the word decay necessarily. Sometimes you do like radioactive decay, but you won't always see that. You see decrease, something like that. But grow or increase, that'll be exponential growth. 8% per year. Well, 1 plus 8% would be 1.08. And the starting value is $200,000, so y is equal to 200,000 times 1.08 to the t, where t is the number of years since 10 years ago. Okay. And the value of the house now, well, now is 10 years after 10 years ago, so I'm going to say, the value of y corresponding to t equals 10 would be 200,000 times 1.08 to the 10. Okay, now, really, I think to get the most out of this example, you'd need a calculator, right? So if you had a calculator, you would see that that number was equal to $431,785. And this brings me to another point that I would like to make to you. This doesn't really have that much to do with algebra, but this is a fact that I can tell you about life that I hope someday will come in handy. And that's that 8% growth doubles your money in 10 years. Okay, that's a mathematical fact. And 8% is something that, a lot of people would say is pretty manageable in certain business and investment contexts. Okay, so based on our model, what was the approximate value of the house 6 years ago? 6 years ago, that would be t equals 4. So I plug in 4 for t in the equation for y, and I see it's 200,000 times 1.08 to the 4, and I type that into a calculator. And that's $272,098 to the nearest dollar. Okay, and I think that's going to be all for you, or for this video for you that you need on exponential functions. I think at this point, you're ready to go on and practice on your own. So good luck with that. Thanks for watching.